I'd like to start by thanking Irfan and the other organizers for the opportunity to speak here. This is a pretty wonderful conference. Nothing like celebrating the contributions of one of the greats of our field to bring together an amazing collection of speakers. So thank you again for that. Today I'd like to tell you about benchmarking progress towards quantum computing. So how do we do that? What methods do we know now we can use? And what are some of the open questions going forward? So the problem is, of course, we're trying to compute with faulty hardware. Our problem is something like this. And we need to know how to proceed. So whenever I show this image, it always reminds me of my master's degree where I was writing a lot of code on a computer that looked a lot like that. And not because I'm that old, but because my supervisor had no budget. And I feel bad for grad students today because you can't really have the cathartic experience with these new flat panel monitors that you could have back then if you couldn't quite find the bug. So we want to ask questions like how much noise do we have and how much noise can we tolerate? And we need robust and scalable methods for answering these questions. So let me start with a kind of a gentle introduction. I'll just introduce some formalism, which many of you know. It'll establish a notation and some comfort level. So we're talking about error processes. Typically when I'm talking about an error process, it'll be the error associated with some gate or some transformation. And I have two different notations I use. One is this scripted E, mathcal E. And here we have this chi matrix representation of the noise. So these are Pauli operators. And also I use lambda sometimes. Now, in this notation, the identity map is this chi0, 0 term, and it would be 1, and all other matrix elements would be 0. But for actual noise, that's not going to be the case. You're going to be populating all these matrix elements. Now, these matrices are d by d matrices, or d squared by d squared, rather. And so that's a lot of matrix elements and a lot of different parameters involved to understand your noise. We want to relate that to practical concepts that we can use in the lab to improve performance. So we want to know in particular, one of the main things is how close is our noise to the identity map, but we'd also like to determine something about the source and type of error. So let's review some simple types of error. So we have a very simple error model called a stochastic error, which consists of just a probabilistic sum of Pauli operators. So notice here that the indices are now the same, so we don't have off diagonal terms. And the simplest example of a Pauli error is a depolarizing channel, shown there, where your noise process either gives you the state you wanted with some probability or the completely mixed state. It's kind of a naive theorist's error model. It's commonly used in fault-tolerant threshold proofs, even though it's not very physically realistic. A more familiar example would be T2 noise or dephasing noise, including when it's T1 limited, and this is a stochastic error, actually. T1 noise is not a stochastic error. And then on the other hand, we have these unitary coherent over-rotation errors. Commonly arises from, say, your control calibration is off, so you're over-rotating about the x-axis. Or you have some systematic detuning effect, or there's some varying magnetic field. These errors tend to be a major problem for a variety of reasons, and I'll be discussing that in my talk. So there's two common figures of merit, or there's one common figure of merit, which is this process fidelity, or average gate fidelity, which involves evaluating how the noise acts on each of the possible pure input states, and then averaging over this Fubini study measure, or sometimes people call it a Haar measure, over pure states. It's commonly used. It's a unitarily invariant measure of closeness to the identity map for that noise process. And then we can just take 1 minus this fidelity to get what's commonly called the average error rate, or sometimes called the infidelity. So this will feature prominently in my talk today. Now, of course, we can reconstruct all the information about our system by using quantum process tomography. I think I was involved in the world record at the time quantum process tomography experiment when I was working with David Corey at MIT, where I helped a grad student do this on a 3-qubit system. And it became clear working on that that was about the worst punishment you could do to a student because there was just so much data, it was so many experiments, it was just a mess. We were really kind of trying to figure out the right way to analyze the data even. But just to highlight some of the issues, of course you get complete information, but skipping to the third point, the information about the error on the gate is tangled up with the errors on your state preparation and on your measurement system. So you get kind of a convolution or a composition of errors, and you can't see the kind of the pure error per gate. Also, you need 2 to the 4 n measurements for n qubits, and you have to analyze these large data sets. So clearly we need better approaches that will work when we're dealing with much larger circuits in the very near future. So what I'll tell you about is randomized benchmarking today, which is, think of randomized benchmarking not as a protocol, but as a family of protocols. And what I'd like to tell you about is that they're quite a bit more powerful and enabling than they were just 5 years ago. So what they allow you to do is fast, easy, and efficient estimation of key figure of merit error estimates, say for your generating gates, your 1 and 2 qubit gates. They also allow a characterization of these control or unitary coherent errors versus stochastic errors, which is a new development I'll tell you about today. The key point here is people are using this a lot for their 1 and 2 qubit gates, but the real value of randomized benchmarking is to be able to characterize large circuits on large numbers of qubits in an efficient way. And another key piece is to be able to use these methods to optimize control over your system, both small and large circuits. And what's remarkable to me is that now we're at a point where we can use these estimated error rates, which are figures of merit, and connect them to the kinds of things we want to, the kind of threshold we want to reach to satisfy the requirements of fault-tolerant threshold theorems. You can't just naively compare this error rate R to a threshold. There's some analysis that goes into it, and I'll tell you about that today. The point is it can be done. And the beautiful thing about using randomized benchmarking is that you can apply it both to your physical qubits and to your logical qubits. So we know that it's hard to understand all the details of the features of your noise on a complex system like an 8-qubit system. It's basically infeasible. It's also hard, if you even knew that information, to figure out how different error correcting codes are going to perform on that error model. I mean, you know they'll eliminate your low weight errors, but you don't really know how they're going to handle the coherent errors and the high weight errors. So what you can do is you can compare the you can integrate those two problems into one problem by looking at the error rates of your physical qubits, choosing a code, looking at the error rates of the logical qubit, and using that comparison to explore the space of possibilities in terms of what's the optimal choice of code given the particular physics of your system. And then I kind of also briefly mentioned we're going to be able to connect the results of these experiments, these protocols, directly to fault-tolerant thresholds. So, benchmarking progress. Here is my collection of reading through, spending this summer in my backyard reading a whole bunch of papers and collecting all the data on the kind of known experiments. You know, if I missed your paper, I apologize. You probably can't tell. But let me just highlight some of the key groups here. So here, notably, these solid squares are the first randomized benchmarking experiment performed by Manny Nil with Wineland's group, and then follow-up experiment. I think this is Ken Brown's experiment, and I just grouped that in with NIST, the NIST work. And then David Lucas over at Oxford did a recent experiment with a startling result of, what is that, 6 nines of performance. So it was actually looking at this paper and being so I'm naturally a skeptic, and I was kind of thinking, well, is this too good to be true? And I read more carefully through Manny's paper, and then I realized that the protocol that Manny developed is not actually the kind of correct randomized benchmarking protocol. He doesn't sample from the Cliffords uniformly. I'll explain why that's important in a minute. I asked my postdoc to do some numerical tests, Joel Wallman. The amazing thing is that if you choose some kind of simple error models like T2 noise and so on, If you use Manny's protocol, it turns out that it overestimates the error. So if David Lucas had done this experiment with the correct uniform sampling of Cliffords, his error rate might actually be lower than this. So I just give you a warning about that. If you want to do randomized benchmarking correctly, then you should refer to some papers I'll quote later, or just send me an email and I can point you to it. Some other things to highlight are the superconducting qubit results. So here, the yellow diamonds, we have results from Yale and then IBM, which I've grouped together because of a continuity of personnel. And here you see a steady increase in performance. And then here in blue, we have Martinez, who's a big fan of randomized benchmarking, was kind of an early adopter. And you see this result here. Let me just point out the IBM results here. What's interesting about this is you get this variety of results. And you're like, well, why are they publishing results that are worse than this one? And it's because what they were looking at was a system with 2 qubits. And they wanted to see some kind of trade-off between designs, which would give good 2-qubit gates versus good single-qubit gates. 2 other things to highlight. Recently, I'm collaborating with Rainer Blatt, and this is our result for his ion trap. And then here is a recent result from Sandia, which shows quite good performance. So these are ion trap results. And then I've just kind of threw everyone else together and the rest. I highlighted the Microsoft result just because I was trying to highlight industry connections here. And so that gives us kind of a sense of where we're at. Also, we have 2-qubit results. So here, this is actually interleaved randomized benchmarking. And what you have is the performance of, this is an initial experiment by the Wineland group. We have the Google results here. We have the IBM results here. And Blatt's ion trap result here. So we see this 0.01 should be understood as 1 error per 100 gates, basically, on average. And of course, people talk about this 1% threshold as some kind of minimum threshold for fault tolerance, but I'll explain why we can't do this direct comparison. So what is the kind of anatomy of an RB experiment? It's actually easy as pie. I mean, at least theoretically, it's very simple. You shouldn't be intimidated. All you're doing is a random sequence of gates. The trick is you want to choose the gates by randomly. It means drawn uniformly from some set, and you have to do that correctly. What you do is you do this sequence of random gates, and then you do an inversion gate at the end, which you can, if you're using the Clifford group, you can pre-compute what this is, no matter how big your circuit is, no matter how many qubits you have. You can pre-compute the correction. And then we imagine some error associated with each gate. And then what we're actually using is the group property of these gates to re-express it this way so that each error is sandwiched between a gate, a Clifford gate, and its inverse. And then we're averaging over all Clifford gates at each step. And this gives us an independent set of twirls. The upshot of that is if you choose your gates correctly, what you get is when you sum over these things, you get a product of depolarizing channels. So you force the noise to be depolarizing. And then you get a simple decay curve. And then the decay parameter P is actually related to this error rate R by this simple formula. And of course, you can efficiently estimate this error rate in arbitrarily large Hilbert spaces. So that's just the standard RB, but now we have a whole family of RB protocols. I would refer you to this work to get kind of the rigorous derivation and description of the protocol. Also, interleaved RB, Izwar is my former PhD student. And this is a scheme where you interleave some gate of interest between each set of random gates, and it gives you a way to characterize the error rate of that particular gate as opposed to an average over the set. Of particular importance is this Unitarity protocol developed by my postdoc Joel Wallman and collaborators. I'll tell you a lot about this today. And we also have this dihedral randomized benchmarking. When you hear Clifford group, you hear this is not a universal set of gates. It's efficiently simulatable. We needed a universal set, at least morally, to do universal quantum computing. Dihedral RB allows you to characterize, for example, a T gate, which you can add to the Clifford set to get universality. It also allows you to characterize any other small angle Z rotation. There's also 2 protocols we've developed to characterize loss, where you lose your system, and coherent leakage, where we have in mind systems where you're using the 2 lowest energy levels as your qubit. Your system can accidentally pop up to the next highest energy level and then come back again. That causes problems. We need a way to characterize that, and that's described in this work. This isn't a highlight of all the work. I'm just highlighting a subset. What's available today is RB protocols to estimate and minimize your coherent or unitary errors. This is a big problem. It's bigger than you think, and I'll explain why. And the idea is we want to do optimization of the control and optimization of the hardware design to really minimize these coherent errors. We have improved bounds for interleaved RB. One of the kind of problems swept under the rug is that there's big systematic errors in interleaved RB that are typically ignored. What we've recently done is found that you can dramatically improve these systematic errors if you do a unitarity RB experiment. It gives you some handle on how badly the coherent noise can combine, and that allows you to get a much better bound. I'll tell you about how to use RB to estimate your worst case error rate or your diamond norm, which is relevant for fault tolerance. And then a really neat result is integrating RB into your runtime execution of an algorithm. So you're going to be doing Shor's algorithm. Instead of doing it the simplest way, we're going to be adding random gates into the circuit. The miracle here is that you can add those random gates into the circuit in such a way that the circuit is unchanged at the end and that you've essentially depolarized the noise. So that's a really cool result, which I'll tell you a bit about today. Work in progress, we want to be able to use the information from these RB experiments or from GST or other methods to be able to project the performance of larger circuits that we can't build in the lab. And so we're developing a system of bounds to do that. That can be applied where you get input data from your generating gates, or you get input data from these small circuit modules like Chris Monroe was talking about recently, and then you'd be able to bound the performance of some different hardware designs for connecting those things based on some assumptions. And I think that would be useful for guiding design. And then another kind of problem that's been hidden under the rug, which Robin has been pointing out recently, is that we actually don't have a good handle on the systematic error for just standard RB even, when the errors are gate dependent, which is of course what's going to happen physically. And recently we have some excellent work in progress. Well, I think it's excellent because we get orders of magnitude improvement in the systematic error bounds because we really just didn't pay attention to it until now. So this is an example of how RB has been used to optimize performance given by the Martinez group, where here they basically do some reference and they have a pulse shape, and what they do is just search through the parameter space to see when they get optimal kind of RB results based on non-idealities in their pulses. It's a pretty straightforward idea. I would suggest that you don't want to optimize just on the RB error rate because it's so insensitive. You want to include this unitarity scheme as well so that you're optimizing based on minimizing your coherent error and not just minimizing your average error rate. So I'm looking forward to seeing some groups do that, and I'd be happy to provide any help in that. Okay. Now, how do we make this connection from these kind of naive average error rates to this granddaddy problem of connecting to the fault-tolerant threshold? So let me walk you through that a little bit. Typically, when fault-tolerant threshold theorems are derived, they use something called the diamond distance, which is a norm, and it's essentially a worst-case error using a norm. They want to know what input state or sequence of states is going to be your worst failure mode. Of course, in a large Hilbert space, you will never actually reach that, so it's a very pessimistic bound. But fault-tolerant theorists also assume the noise is depolarizing, so it kind of doesn't matter. And on the other hand, we have this quantity which is experimentally accessible, as I've just told you, which is this average error rate R. And there's some really neat work by Joel Wallman and Steve Filmia where they found these bounds. This lower bound was known previously, and they found this upper bound. And what you can see here is that if you measure this experimentally, then this factor is basically 1. And so the lower bound they're essentially the same thing. The upper bound, you get this huge factor of the dimension of the Hilbert space. That's the first problem. The second problem is you get a square root of R. That's really bad. So if your error rate, if you benchmark your system to have a 10 to the minus 4 error rate, square root of R is 10 to the minus 2. So now all of a sudden you're saying, well, I have, a qubit, and so this is, 2 times 10 to the minus 2 is what I should be comparing with my fault-tolerant threshold, because that's the best upper bound I have. So we can only get a very loose bound and essentially a useless bound on the diamond distance from the RB error rates alone. So the lower bound, how do we get that nice lower bound behavior? Well, the lower bound is saturated by stochastic noise, by what poly noise that I showed you earlier. So then essentially your RB rate is your worst case error. The upper bound scaling with square root R is saturated when you have these control errors, these unitary errors, these over-rotation errors. So that's part of the problem. I mentioned the problem is worse than you think. This is one part of the problem. One part of the problem is that your ability to bound the diamond norm is horrible when they're unitary errors. The second part of the problem is that the fault-tolerant threshold itself is much worse if you can't promise me that the noise is stochastic. So you have kind of the target gets harder to reach, and you have a worse estimate of that target. So you get two hits at being able to compare to fault tolerance. So just to give an example, suppose you measure this 10 to the minus 4 problem. Suppose that, I mean, when I talk to experimentalists about this, I often hear, oh, my coherent noise isn't a problem. I know that it's 10% or 5% of my total noise, so it's not my biggest problem right now. Well, it is your biggest problem, because here we have 17% of the noise is due to this rotation error, but the worst case error is 10 to the minus 2 because of the square root of R. On the other hand, if you were able to polytwirl that noise and make it stochastic, then your worst case error is 10 to the minus 4. Let me just drill this point home with some plots. This is basically the same point. You imagine that you have X% contribution of your total error rate is from coherent errors, where X is small, 5% to 0.1%. And here's how your bound performs. Your bound of the worst case error gets really bad. You get essentially an order of magnitude worst estimate when you go from, well, you can interpret the figure, but basically even small amounts of coherent error, for example here, 0.5% of your noise is coherent error, well, you get an order of magnitude hit from that 0.5% coherent error. So we got to get rid of it. We got to engineer it away, and we got to use software techniques to get rid of it. So how do we first identify it? How do we find this beast? Well, again, this is work I wasn't involved in. It was Joel Wallman and collaborators, and they identified this quantity called the unitarity, which essentially characterizes what they call the unital part of the process polytransfer matrix, and it ends up being a very good measure of the amount of unitary noise you have. And in our collaboration with Reiner Blatt, they actually did this experiment. It's basically as easy to do as a randomized benchmarking experiment. And they got this number for the unitarity, this number for the decay rate, and then they get this bound of essentially a 10% diamond norm, even though they have almost two nines of fidelity. So this is another example of the hit you get. And I show you the experiment because experimentalists like to see that it's doable by actually knowing that someone did it. So there, it's done. Now the last piece of the talk I'll tell you about is this randomized compiling idea, which I'm really excited about. This is a little bit before its time because we're not running Shor's algorithm yet, but just to let you know that there's hope. So what we worked out, and this is Joel and myself, that if you have some algorithm, even a universal, it doesn't have to be a Clifford algorithm, but a universal circuit, there's a way to, so these are different rounds of the circuit. You divide it up into single qubit gates, your 2 qubit gates, single qubit gates, 2 qubit gates. Each of these is then one cycle, one clock cycle. And then what we do is we take the base circuit, this could be say Shor's algorithm or whatever you're doing, and then what we do is we add random gates in a controlled way. And these gates, after the 2 qubit gates, are chosen carefully. And you can pre-compute this on the fly in a scalable way. That's the beautiful thing. And you add all these in, and you think, well, you're increasing my circuit length. I don't like that. Well, first of all, it's just a factor of 2, but it doesn't even matter because it's a factor of 1. Because then what you can do is you can just compile these random gates into the circuit and execute this randomized circuit. And it turns out you can do this in such a way that you can reinterpret your bit string at the end according to what it would have been for the original circuit. Much like Manny talked about in his toggling the poly frame. But this is a generalized version of that. And The trick is you divide your circuit into easy gates and hard gates, and the hard gates go here and the easy gates go here. Typically your hard gates would be 2-qubit gates, but they could also include your T gate, for example, which you've injected via magic state distillation, and typically would have a much worse error rate, say, than your simple Clifford gates on single qubits. And kind of magically this all works. And let me just explain a little bit more about how this works. So you would have a twirling scheme where there's two different scenarios. One would be your hard gates correspond to your multi-qubit gates, and your easy gates are your single qubit gates. In that case, the random gates you insert are poly gates or these dihedral gates, which is a dihedral group. I don't have time to explain it, but it's basically simple rotations around Z plus bit flips. And another scheme is you might do this at the logical level. You would have your hard gates are controlled Zs and the T gate, because they've been injected, and so they're going to be really noisy, so say. And then your easy gates would be the single qubit Cliffords. And then the twirling gates would be this dihedral group. And this is relevant when you have transversal Cliffords and a logical T gate for magic state injection. And it works with many other scenarios, which I can't describe here. And this is what it looks like in practice. This is a lot for you to absorb. So this is trying just to show you we've worked out all the details. And the key fact is that this box here is the noise from your easy gates. And this box here is your noise from the hard gates. And then what you end up doing is twirling the composite noise to depolarize it. Let me just skip that, and I'm running out of time, so let me just give you the mathematical result and then show you some numerics. So the key point is that we upper bound the diamond norm, we get a product of square roots. So you get, remember the square root of r is bad, but here we have two square root of r's multiplying each other. And so what we're doing is we're modulating the error rate on the hard gates with the error rate on the easy gates. And that's how we get a really good bound on the total performance of the circuit. And so it's effectively linear with R. And we have two bounds. This one works well when your easy gates are really good compared to your hard gates, which is what we expect to be the case. And this is what you get. So here, this is completely realistic modeling where all the gates have gate-dependent noise, and we just went nuts with giving ourselves a hard time. And what you see here, this is the lower bound that I showed you earlier. This is what your worst case noise would be. So here the y-axis is your worst case noise, your bound on it. And the x-axis is your benchmarking error rate. What we're looking at here is 10 to the minus 2, and down here would be 10 to the minus 3. And now, if you had stochastic polynoise because of some miracle, this would be your bound on the worst case scenario. If you have nothing about your noise other than the error rate, this would be your upper bound on the worst case error. But if you know that your error rate on the easy gates is 10 to the minus 3, you get this much of improvement. If your error rate on the easy gates is 10 to the minus 5, you get this huge kind of more than one order of magnitude improvement in your bound. And these results get better as our systems get closer to ideal. How much time do I have? A couple minutes? 1 minute? 0 minutes? All right, well, I'll just skip this, but basically I'll tell you a little bit about our scheme for predicting computational capacity. It essentially uses the unitarity and the RB error rate to define this coherence angle, and then we can bound the C as some circuit you're interested in, and we can upper bound the infidelity of the circuit based on these inputs from the individual elements of the circuit. And essentially the bound works well if you can show experimentally that your coherent noise is small. And so this is a way to do that. And this is improving the systematic error on interleaved RB, which was badly needed. Here we get, if you show that your coherent error is small, you get a huge improvement in your bounds on the performance of interleaved RB. And I will end there, and this is just a summary of what I've told you. So thank you for your attention.
Questions for Joe?
Yeah, can you perhaps give us some more intuition as of why interleaving your hard gates with these more simple gates gives you the multiplication of errors, and why does it help you?
Let me tell you at least about a feature of it. One feature of this result is that it's robust to, if the gate-dependent errors on your hard gates are bad, So your C naught between qubits 1 and 17 is good, but your C naught between qubits 1 and 87 is horrible. Or just the point is you're going to get a huge variation in your 2-qubit gate error rates. If you do this scheme, you become insensitive to that dependence, which is a feature of it. As to why it works, I mean, intuitively what you're doing is by inserting randomness, by inserting these controlled random gates from these 2 designs, which is what gives you depolarized noise, you're essentially forcing the noise to be more stochastic. And that's really the key. It is just, you know, after we came up with this work, I was trying to look, has anyone come up with this idea before? I mean, these ideas exist in dynamical decoupling. Manny was hinting at these ideas, and so the idea is out there. Lorenza has worked on this kind of thing, showing that introducing random gates improves performance dramatically. Oh yeah, I should mention one of the really big benefits of this that actually some colleagues of ours have done experimentally and shown is that it dramatically reduces your non-Markovian noise. And just like coherent errors are a big problem, non-Markovian errors are a huge problem because we don't really know how to handle them. And this type of scheme, just like dynamical decoupling, it suppresses non-Markovian noise in a very dramatic way. And so that's another kind of benefit of this. But as far as intuition, it's just like dynamical decoupling. I feel like our contribution was to show that it worked for universal circuits and to show that it introduced no overhead, because everyone else is imagining throwing in these gates. We're saying, well, you throw them in, but then they go away. They're just virtual. And what it means is you have to compile the executable multiple times. So I'm running Shor's algorithm. I'm going to be collecting statistics. I'm going to run it 1,000 times. Well, each time you run it, you're going to run a different executable. So that's the overhead, which is just post-processing or classical pre-processing, which is linear with the number of samples. It's not depending on the system size.
Other questions? So while Irfan's running over, maybe I'll ask one in the interim. So something you alluded to, Joe, was the importance of sort of uniformly drawing from unitary 2 designs.
Yep.
But recently, I guess I've seen a couple places where they've cropped up where people have been looking at generalized sort of RB schemes, where they try to kind of relax this Unitarity 2 design sort of condition. Can you give us some insight or intuition as to when is that the right thing to do? Sort of when does that work better? Sort of what's the kind of baseline for that?
Yeah, sure. Well, the dihedral RB I told you about relaxes that condition. Martinez did some work looking at more generalized 2 designs based on these Platonic solids. The key point is that you have this complex process matrix, and any kind of twirling, what it's going to do is it's going to, first of all, throw away the off-diagonal elements if it includes the poly group. And if it includes other groups like Clifford group, it's going to coarse grain the information along the diagonal so that you can sample from it and learn about the noise in an efficient way. And these other approaches, which weaken the 2 design condition, they're creating different IREPs. And then the idea is you can just sample from those IREPs and still actually get pretty reliable information.
So you had a comment about taking a hit twice with coherent errors, once from the square root factor in the bound on the diamond norm, and once from a difference in the threshold. So I wanted to follow up on that because I only know of about 3 or 4 examples in the literature of schemes where a threshold has been derived both for stochastic and for general noise for the same scheme. And in all the cases, the thresholds are the same, actually. They're just in different units. So is there really a second hit there?
Oh, so yeah, you know, I'm not an expert on fault tolerance. I just know that like Dan has a draft textbook out there, and you know, I've read that, and he's pretty clear about, you know, if Dan says it, I trust it. And we're talking about Dan Gottesman, sorry. And Dan, you know, makes that argument at the end of the book that this is, he basically, what Dan suggests is this, and he's probably right, because he usually is. He says that, look, we're worried about coherent errors in this context because you're worried about this worst case accumulation, where essentially the coherent errors will align in a mischievous way so that they accumulate along the same axis. And that's where you get this quadratic growth of error instead of linear. And that's one of the problems that people worry about. It turns out, we've done some numerics, and that doesn't really happen. You don't really get the quadratic growth. It's really a conspiratorial thing. And one way to think about this randomized compiling scheme is that it's suppressing that. Because if the errors are going to combine in a deleterious way along one path in your circuit space, that's only going to be along that one path. Other paths, they won't align. They'll kind of cancel each other out. And so by doing this randomized compiling scheme and running the circuit with a bunch of different random realizations, you're explicitly suppressing that to have a small contribution to your total error. But yeah, it could well be that, in fact, the threshold isn't worse. I just know that we don't know that much about it. There's not enough results. But I'd be happy to hear about that work, actually.
So it's my understanding that randomized benchmarking can only be used with Clifford gates. What's the outlook for non-Cliffords?
Oh, yeah, so I mentioned earlier that this dihedral benchmarking thing drops the Clifford assumption. And in fact, I have a slide on it here. Oh. All right, I put the slide after end document, so it's not showing up. But basically, the dihedral group is just, it's bit flips, X flips, and then Z rotations about small angles. And that's exactly what the T-gate is, right? It's a pi/8 rotation. And so it turns out, like I was saying earlier, that when you do that kind of a twirling scheme in an RB scheme, what it does is it reduces the error to a block diagonal form instead of it being a depolarizing channel. And then it turns out, and this just, we didn't realize this till recently, it's actually straightforward how to sample from that block diagonal structure to get the useful information out. So it turns out the two-design condition wasn't really that necessary. It was just the simplest thing to do. So in fact, you can relax it.
We're running a little bit late, so why don't we thank Joe for a very interesting talk.